Hi, welcome to the session Indexes in Oracle. This is the part 2 of Indexes in Oracle video tutorial, and in this part I'll discuss about B-tree index types. I'll discuss about different type of B-tree index. Different type of B-tree indexes are descending index, key compressed index, reverse key index, B-tree cluster index, and index organized table or IoT. We'll discuss about each of these types. Only for IoT we'll discuss a bit briefly, cause in a later part we'll discuss in more detail about IoT. What a descending index. In case of B-tree indexes, by default data is stored in ascending order of the index key. Suppose character data is stored by order of the binary values contained in each byte of the value, and numeric data from smallest to largest number, and date from earliest to latest value. Now you can create a descending index by specifying the desc keyword in the create index statement. In this case, the index stores the index data in descending order. In this case, the rightmost index leaf will have the lowest values and leftmost leaf node will have the maximum values. For example, this is the diagram of a B-tree index. By default, the data is stored in ascending order. You can see in the leftmost leaf node the values are like 0, 1, 2, 3 and like that. In the rightmost there are the bigger values, maximum values. In case of descending index, that it will be reverse. It will be just opposite of that. Okay, in the leftmost it will have the maximum values. In the rightmost part it will have the minimum values, lower values. Okay, so let's check how it works. Before that, another thing I want to say, descending indexes are useful when you are using a composite index on some column, some 2-3 columns, and the query sorts on some column in ascending order and others in descending order. Let's check the use of descending index. Before that, we'll create a table TOBJ as select star from all objects. We'll create a normal ascending index, a B-tree index, and we'll gather the statistics. Let's execute the query. We'll select object type, object ID, object name, these three columns. These three columns are indexed from this table, where object type equal to this, object ID less than 1000, and we'll do a descending order of these three columns. Let's see what happens. You can see it is doing index range scan descending, and then it is giving us the data. Okay, so this means that Oracle has ability to scan the index in descending order. Okay, by default it is ascending, but let's see the difference. Now I will execute another query. In this case, object ID I'll be facing in ascending order, other two columns in descending order. Let's see what happens. So here it is doing index range scan, then a sort order by to give you the sorted data, cause two columns I am ordering by descending and particular one column in ascending order. Okay, so let's drop this particular index and create a index, descending index. I'll specify this desc keyword in last. Index created. Let's gather the statistics. Okay, I have created a descending index. Now let's execute this query again. So this is the same query I have executed earlier. Now it is just doing index range scan. It have eliminated a step, sort order by. Okay, so it have the ability to, like, I have created the index, these two columns were in descending order and this particular column was in ascending order. This was the statement. So in an additional step of sorting is here eliminated. So this is the benefit of descending index in this kind of queries. Let's discuss about key compressed index. Another interesting feature of B-tree index is index key compression. Creating an index using the key compression feature enables you to eliminate duplicate occurrence of index key values in B-tree indexes or IoT. And key compression is very much useful when the database deals with duplicate values in the index keys. It will be helpful in cases like you have a composite index or IoT, and in the IoT or composite index will be lots of duplicate entries, and you may use this key compression feature to eliminate the duplicate by using a key compressed index. So the basic idea behind index key compression is that every index key entry is broken into two pieces, a prefix component and a suffix component, and the prefix is built on the leading columns of the composite index and will have many repeating values, and the suffix is built on the trailing columns in the index key and is unique or almost unique component of the index entry. And database achieves compression by sharing the prefix entries among the suffix entries in the index block. Typically, when you create a normal composite index, the index entries will look like this. Suppose I have a table, I have created a table tobj as select star from db objects, and I will create a composite index on owner, object type, object name, these three columns. Okay, index created. Now if you see, this three column will have many duplicate values. Among these three, the first column owner will have many duplicate values, and object type will also have duplicate values, and object name will have very less duplicate or almost unique values. Okay, so once we create this index, conceptually a non-compressed index leaf block looks like this. Okay, it stores this index key and row ID like this diagram. Like, once we have created this index, conceptually the leaf block entries will look like this. There will be owner, object type, and object name, and row ID that is pointing to the specific row in the table segment. Like here, sys procedure name and the row ID, sys procedure name and the row ID, and sys package name and the row ID. In a non-compressed index, it will typically look like this conceptually. So now I will do this: analyze index name, validate structure. It will populate the index stats. Okay, and like we need to do this operation. Like I will create several several compressed index with different compression degree, like compress 1, 2, 3, and so index stats will be updated once we validate the structure, and old value will be removed. So I'll create a temp table, and I'll store the current state of index stats into this. So in the index stats view, from the index stats view, we can see the height, leaf block, branch block, BT space, and OPT CMPR count and OPT CMPR PCT save. These two are very much vital and related with compression. I'll discuss about this particular two columns. Okay, so let's create a temp table T index stats as select star from this particular view. Okay, here B-tree space will be the total space in the index. Okay, so now the entry looks like this particular diagram. Now I'll create another, I'll drop this particular index, drop index non-compress, and I'll create a key compressed index with compression of 1. Okay, okay, now I'll populate this index stats, T index stats. Okay, now if you look from T index stats view, you have two entries. This was the first index, non-compressed one. Here you can see we have used the compression degree of 1, and number of leaf blocks have reduced, and number of B-trees, the amount of B-tree space is also reduced from this amount to this amount. Okay, and now I'll discuss about this particular two columns. This OPT CMPR PCT save, this represents what will be the optimum compression percent saved. Okay, that means you can if you use the compression of 2, it will be the best compression count for this particular index. Okay, and OPT CMPR PCT save, this represents what is the number of what is the percentage of save space you can save using index key compression. Okay, the at first it was 28, that means you can save 28% of space from this index using index key compression. And what will be the compression count? 2, and at this moment it is showing as 19. That means we can save like we have saved some space using compression 1, and we can save about 19% of space more. Okay, so we have now created a key compressed index with compression 1. Okay, this represents this means the prefix length will be 1, prefix will be 1 here. Conceptually, if you create this compress 1 index, then it will look like this. Here prefix entry will be there once on the leaf block, not once per repeated entry. If we use this compression, each suffix entry references a prefix entry which is stores in the same block as the suffix entry. Like here you can see conceptually, if you think prefix will be sys, we have used this compression 1, and index in the leaf entries the values will be like this, suffix entry values will be like this, procedure, then procedure name, then row ID. Previously it was like this in a non-compressed index. Okay, now we'll drop this particular index and we'll create with compression count of 2, and we'll populate this. We will analyze this particular index and validate the structure, and then we'll insert into our temp table. So let's check, select star from T index stats. So here you can see leaf blocks have reduced much more using this compression count of 2. Okay, and B tree space have reduced very much. Okay, and this particular OPT CMPR PCT save is showing 0. That means you cannot save any more space if you use a larger compression degree. You have saved all the space you could save using the compression. Okay, so now it looks like this conceptually. In prefix you will have this object, you will have this owner and object type. In the suffix entries you will have the object name and the row ID. Okay, this is the conceptual diagram. Okay, and here each suffix entry will point to the prefix entry. Here prefix entry is owner and object name. Now suppose if you use compress 3, I'll drop that index and create another index with compress 3. Okay, so let's see. Here you can see the number of leaf blocks have actually increased from the first one. In the non-compressed index it was 523 and it is now 586. The B tree space have increased for okay, it was previously around like 42,16,000 and some 128. Now it is around 47 lakh. Okay, and this OPT CMPR PCT save is showing as 35. Okay, that means it is not the optimal compression you can do. Thus compress 2 was the best one. Okay, And actually this 35 means this like from the last compression, like compressed to the amount of space was there in compressed to, you have increased by 35%. Okay, from this last, like this value is larger, almost large as 35% from the last one. Okay, it was 30 lakh and it is now 47 lakh. It is 35% increased. What is the reason behind it? If we use the compress 3, then conceptually it will look like this diagram. Prefix entry will contain all the columns, like here owner, object type, object name combination. By using compress 3, it will add object name in the prefix entry itself, which will make it almost unique. Okay, therefore it's like adding a additional prefix entry to almost all index key and making it almost unique. Because of this, number of lib blocks and the size of index will grow. Okay, and another thing, you can, if you don't specify any key, any like compress 1, compress 2, compress 3, and if you just mention as compress, then what will happen? Now I'll drop this index again and I'll create another index with just keyword compress. This index is created, so let's look. This is default compression. Here you can see there is no difference in default compression and the compression amount of 3, compression degree of 3, like there is no difference. So it is same as compress 3 in this case. It is compressing the maximum compression that it can do, but it is not the optimal compression. The optimal compression will always be 2 here. Okay, so this was the key compressed index, and using key compress index, you can reduce the index storage space. You can see how can like how you can reduce the index space. Okay, and in using key compress index, in the key compress index there will be more index entries per lib block, so it can reduce the logical IO, latching, and increase the buffer cache efficiency at same time. And this reason also can cause block contention on frequently modified tables, and it can take little more CPU process to use index in some cases. The reason of block contention is in single lib block there will be more data, so so this is one reason of the block contention. So this is I wanted to cover about key compressed index. So let's discuss about reverse key indexes. A reverse key index is a type of B-tree index in Oracle that physically reverses the bytes of each index key. They were implemented to reduce the block contention on index lib block in indexes, specifically on columns populated by sequence values, especially on Oracle rack environment. So basically this is the structure of a B-tree index. Okay, and indexes store sorted value based on key, order of key, and there will be in the leaf node there will be pair of key and row ID. Okay, meaning the values in the index will be arranged in order of ascending or descending. Okay, in case of unique key or primary key columns, when populated by sequence based key values, recent entry will be placed in the rightmost lib block of the B tree as the data is ordered, suppose in case of ascending index. Okay, now all new data will be stored in the rightmost lib block of the index. As using sequence more and more session inserts rows to the table, the rightmost lib block will become full and it will become the hot block. Then Oracle will split the block, that rightmost lib block, into two lib blocks, one block with all rows except one row and a new block with just one row. And now this new lib block becomes the rightmost lib block and the concurrency moves to the new lib block. This kind of index growth is termed as the right hand growth indexes. As more and more session inserts to the rightmost leaf block of the index, it becomes the hot block and causes contention on the leaf blocks, which leads to buffer busy wait. Because they are in the same block, more and more sessions are trying to put some values. More and more sessions are trying to insert values, which can lead to buffer busy wait. In Oracle rack environment, the problem can become dangerous while inserting values from sequence. That hot rightmost index leaf block will be transferred between the different instances. If the block is considered busy, then LMS process might induce more delays in transferring the blocks between the instances. While the block is in transit, then the sessions accessing the block will face buffer busy waits, GC buffer busy wait, and excessive GC buffer busy wait can cause very much significant performance issue. So reverse key indexes are designed to resolve this kind of issue related to index block contention. It physically reverses the bytes of each index key, while DML operation reverse key index simply takes the index column value and reverses the key value, then inserts into the appropriate leaf node. And reversing the keys of the index allows the insertions to be distributed across the leaf nodes in index, which can make insertion far faster because there will be no block contention. Now how the reversing is works. Suppose if you look in the rightmost leaf block in the diagram, the value is 368, 369, 370 and then 371. These values are populated, consider these values are getting populated using sequence. Now the internal representation of 368 will be C2 445, and for 369 it is C2 446, 370 C2 447. You can see the first two values like C2 4 is same across these all index keys, and only the last values changes 45, 46, 47. So when some insertion request comes and the insertion value, the index key value, it is populated of 368, Oracle sees it as 45 4 C2. For 369 368 it sees as C2 445, for 369 C2 446. And as in ascending index or descending index, they are in some ascending or descending order. Suppose in case of ascending index, it will see it as C2 445. Okay, the next value is C2 446. Okay, the next value is C2 447. Let's put them in the same block. When the request will come for C2 446, it will insert in this particular leaf. When the request come for C2 447, it will place in the same block. Now in case of reverse key indexes, Oracle will reverse these values. Now C2 445 will become 45 4 C2, and C2 446 will become 46 4 C2. So these values are not adjacent anymore. So this is the way Oracle will distribute, like C2 446, when the insertion will come, it will become 46 4 C2, and Oracle might place it in another block where according to the particular order. And C2 447, it will become 47 4 C2. It will not be placed in the rightmost block, maybe it will be placed in here. And for another value like for 371, suppose the value is C2 448, and then Oracle will reverse it as 48 4 C2, and Oracle will check in some block, and it will place in some another block, not in the rightmost leaf block. Okay, so based on the reversed value, the order will be maintained, but based on the actual index key values, there will be no order. Okay, so this is how basically reverse key index works. And as the new values are inserted and the insertion is distributed across all different leaf nodes, there is no block contention on the rightmost leaf node. Okay, this is the way you can eliminate the buffer busy waits, and it will make the insertions very much faster. While DML operation, reverse key index simply takes the index column value and reverses the key value and inserts in the leaf node. Reversing the keys of the index allows insertion to be distributed across all the leaf blocks in the index, which can make insertions faster because there will be no buffer busy wait. As index is not sorted by column key anymore, they are reversed and inserted. One problem with reverse key index is processing range predicates in your query. While using reverse key index, CBO may ignore the reverse key indexes while processing range predicate. Okay, so this is one problem with reverse key index. So let's discuss about B-tree clustered index. Clustering is a feature in Oracle using which you can store a group of tables that share some common column in the same database block, and you can store the related data together in the same block. With a cluster, a single data block may contain data from many tables. You can create a cluster key on the common column. Clustering is very much useful when you have some tables with some common columns and frequently you use that particular column to join the tables to fetch the data. The cluster index is a B-tree index on that particular cluster key, and a cluster index must be created before any rows can be inserted in the clustered tables. Think about a scenario like there are tables, employees and departments, and you use department ID to join these two tables, and you join these tables and fetch the data very frequently. Okay, now for this kind of scenario you can consider creating a cluster, and you will create a cluster key on department ID, and you will create a clustered index, B-tree index on this department ID, and you will create the two clustered tables, employees and department, on the cluster. So let's do that. I'll create a cluster, create cluster, cluster name. You have to specify the cluster key dpt id. Cluster created. Now you will create the clustered B-tree index. Create index, index name on cluster, cluster name. Index created. Now you will create the clustered tables. Create table, table name. You will specify all the column names, and you have to specify the cluster name and the cluster key. Now I will create another table dptc on this cluster. Same syntax. So I have created a cluster. The cluster key is department ID. I have created an index on this particular cluster, and I have created two tables on the cluster. So how it works actually? This is non-clustered tables in this diagram, and here data blocks from the departments table will be stored in different segment, dpt segment, and from in the employees table, for the employees table it will be stored, the data blocks will be there for the employees segment. They are stored separately in typically non-clustered tables. Now this is the diagram for clustered tables. Like below example, all the rows from EMP for department ID 10 and the rows from DBT for department ID 10 will reside on the same exact data block in the cluster. Because of this, fetching the data using join, you have to do much less IO, because in the same block you will get everything from department, from the employees. Okay, and using this index key dpt id or department ID, you can fetch the data, and you can create a index on this cluster key, and this index on is typically called as the clustered index, and it is used to locate the blocks. The cluster index is a B-tree index on the cluster key. A cluster index must be created before any rows are inserted in the clustered tables. First you create the cluster, then the clustered index, then the tables on cluster. Finally you insert the rows on the tables, and the database physically stores all rows from these two tables in the same data blocks, and the database stores rows in the heap and locates them using the index. The B-tree cluster index associates the cluster key value with the database block address or DBA of the block containing the data. For example, the index entry for the key 20 shows the address of the block that is containing the data for for employees in department 20. So this is how basically this clustering stuff works. So now I will discuss about index organized table or IoT. I'll just briefly discuss about IoT in this session, cause in the next part of the video tutorial I'll discuss IoT in very much detail, cause IoT is a big concept. Okay, an index organized table or IoT is a type of table that stores data in a B-tree structure. In a traditional heap organized table, it holds the unorganized unsorted data, but the data is in the IoT is stored and sorted by the primary key. In IoT there will be a primary key. Okay, in IoT rows are stored in a B-tree structure. In IoT the B-tree leaf blocks also stores the non-key column values. Thus IoT stored the index along with the data. Since there is no data segment, there is no physical row ID concept for IoT, although there is concept of logical row ID. I'll explain in the next part of the video tutorial. So just take a look how IoT works. Index organized tables are useful when related piece of data must be stored together or data must be physically stored together in a specific order. IoT contains the index columns and also the other columns in the leaf node. Unlike the normal B-tree index leaf nodes, contains only the physical row ID address of the particular row you are searching. So if you are searching for a particular row in your IoT, it will just traverse through the branch to the appropriate leaf node and will get the data for you. Because of this, there will be very less number of IO. For example, if you can see the diagram, this is the typical conceptual structure of index organized table. Here in the index leaf node, you have the index key value like 101, 102, and also the other data for the other columns that are not indexed. Okay, so everything you will get here. You don't need to visit a table block. Typically when you issue a SQL statement to select row via index column, then Oracle will first read the root block, consider it is a B-tree index, then it will find a relevant block with the first level of branch, then it may go for the other branch levels if there is other branch levels, and then finally the relevant leaf block. For example, if you see this particular diagram of B-tree index, suppose you want to locate the data for employee ID 170. The journey will begin from here. It will visit this block 170, then it will go to this particular branch block, then it will go to this index leaf block where it will get the row ID and it will access the table here using the table access by index row ID method. It will get the data from the table segment. Typically it will do 1, 2, 3, 4 number of IOs. Okay, but what happens in IoT? If you are using IoT, first the journey begins from here. Suppose you are looking for some data where this ID equal to 100, 101. Then the journey will begin from this root node, number of block visit 1, then it will get to here, number of block visit 2, then it will get to here, number of block visit 3, and from the leaf node itself it will get the data. So there is no need for table access by index row ID, no need to go to the additional any table segment. So you can see there is less number of IO, less number of block visits. Okay, so this is the basic key concept of index organized table, and in the next part I'll discuss about index organized table in bit detail. Okay, so this is what I wanted to cover in this session, the different type of B-tree indexes.